All right, welcome to our second video in our tropical cyclone motion series. In this video, we're going to take a look at large-scale controls on tropical cyclone motion. In particular, we're going to look at how we can define that large-scale wind that we have previously said is the predominant factor that steers tropical cyclones. So let's dig in. So recalling our basic climatology, where we said that the climatological tropical cyclone tracks roughly follow the periphery of the climatological subtropical anticyclones, we said they move with the wind. But how do we actually define the wind? So that's the goal of this video, is to define what that wind actually looks like. So let's take a vorticity tendency approach. So first, let's define those words and what we mean by this. So a tropical cyclone can be viewed as a vorticity maximum, a cyclonic rotation maximum. It's possible to have anticyclonic vorticity or vorticity minimum in those cases. However, we're going to look at a tropical cyclone as a cyclonic rotation or vorticity maximum here. So, given this, if the tropical cyclone moves with the large-scale wind, the vorticity tendency, which is the change in vorticity over time at a given point, should be dominated by horizontal advection. So let's say that I have a point here, and my cyclone is over here, and I have some wind that is trying to move it toward that point. So at that point, the wind is increasing the cyclonic vorticity as the tropical cyclone is brought closer to that point. So we define that as cyclonic or positive vorticity advection. And so again, ahead of the cyclone, that vorticity tendency should be positive. The wind is moving the tropical cyclone. I think I had it this way. I forget exactly how I had it, but the wind is moving the vorticity maximum, or the cyclone itself, toward a given location. So behind the cyclone, you'd expect the vorticity tendency to be negative, but we're not particularly interested in that here. So what we have on the left-hand side here is an application of the vorticity tendency equation with a whole bunch of different forcing terms. And I've pulled out the two that are particularly important here. LC, or the local change in vorticity with time, this is the vorticity tendency itself. This is what we're trying to diagnose. HA is the change due to horizontal advection, and they're given by the red and the green lines respectively. And once you get above about 900 millibars, but below the tropopause, roughly around 200 millibars in each of these three panels, whether a cyclone is moving slowly, moderately, or fast, the HA and T lines very close, or sorry, the HA and the LC lines fall very closely to one another, whether it be slow, whether it be moderate, or whether it be fast here, which suggests that the total vorticity tendency, the total change in vorticity out ahead of the tropical cyclone, is primarily governed by horizontal advection, which leads us to say that the large-scale wind that advects or moves the cyclone from west to east or east to west, depending upon the particular latitude, is the predominant factor that governs tropical cyclone motion. We can't tell specifically just what percentage of that we see here, but on average, when you do that type of diagnosis, it's between 60 and 80% of all variability in tropical cyclone motion is governed by the large-scale wind. And we can see that this correspondence between the local change in horizontal advection lines is pretty good above the surface layer, above the boundary layer, until you get up toward the tropopause, with some variations in just how strong that vorticity advection is, or that vorticity tendency is, that scales with the actual wind speed steering the storm. So this gives us some clue that perhaps the tropospheric deep wind, or some portion thereof, excluding the near surface layer, the boundary layer, may be a good approximation for that wind that moves the tropical cyclone. So we define this as our steering flow. Again, tropical cyclone motion can largely be conceptualized as motion or steering by that large-scale wind, especially above the boundary layer. We call this our steering flow, and in specific, the steering flow is the vertically weighted large-scale wind averaged across the cyclone when you exclude the cyclone's own winds. So you have the cyclone here, and you take some area around it, and you average the horizontal wind, and you weight it vertically above the boundary layer but below the tropopause, with some variation as a result of cyclone intensity that we'll talk about momentarily, and this gives you the steering flow for the tropical cyclone. Again, just as I noted, the layer over which this steering flow is computed varies as a function of cyclone intensity. Why that might be the case? Keep in mind that cyclones have their strongest intensity near the surface, and they decay in intensity as you move upward from there toward the tropopause, where the cyclonic circulation has completely eroded and given way to anticyclonic outflow. In general, the more intense the cyclone is, the stronger its reflection going up in the troposphere will be. A weak tropical cyclone will not have strong rotation above the mid-troposphere, whereas a very intense tropical cyclone will have intense cyclonic rotation as you get up even close to the tropopause level. So as a function of that intensity, due to the warm core structure, the winds decaying with height of a tropical cyclone, you get a different layer over which this vertical weighting is done as a function of tropical cyclone intensity. So our friends over in Madison with this tropical cyclones group there have this nice little chart that they've put together that shows different pressure levels here on the y-axis and different tropical cyclone intensities here on the x-axis, roughly binned in 10 millibar increments. 1000 to 1010, 990 to 999, et cetera, down to less than 940 hectopascals for the minimum sea level pressure. So for these really weak tropical depressions, weak tropical storms, you're looking at a steering flow that only extends between about 850 and 700 hectopascals. But as the cyclone's intensity increases as you go further to the right on this diagram, in general you extend that steering layer to higher and higher altitudes, such that 940 to 949 millibar minimum sea level pressure is an 850 to 250 hectopascal steering layer or steering flow. Even deeper storms start to get above the boundary layer because the influence of the cyclone itself, the pressure is so low that the extent of the boundary layer goes to a higher in altitude pressure surface because the pressure surfaces are also close to the ground compared to common conditions when the cyclone is weak. So for those, you're looking at 700 to 200 hectopascals. This is all based off of a historical analysis. If you take a large number of tropical cyclones, if you take the large scale wind associated with them and average it over these different layers, which one or ones gives you the best fit to the observed track data? And that's where these different bars come from. These are the steering flows or steering layers that give you the best fit to where the tropical cyclone would actually track in the subsequent 1 to 2 day period. So we can take a look at a couple of examples of what this steering flow looks like. We had our atypical first ever in April tropical cyclone in the eastern North Pacific a week or so ago in the form of Tropical Depression 1E. We have the low-level steering flow, which is appropriate for that weak system with a sea level pressure between 1000 and 1010 hectopascals. So we're looking at the layer averaged flow between 850 and 700 hectopascals here. We see the subtropical anticyclone to the disturbances north and west. We see the cyclonic flow associated with the disturbance itself. We see a deep area of low pressure in the Gulf of Alaska here with strong low-level west to east flow in the mid-latitudes impinging upon the Pacific Northwest and the British Columbia coastline. We see a trough over the central United States just to our south here as well. So we would expect this tropical cyclone, given that it is in an environment of relatively weak steering flow, with flow primarily directed from east-southeast to west-northwest in its immediate vicinity toward this subtropical anticyclone, would move relatively slowly toward the west-northwest. But what if it were more intense? We can look at a deeper layer steering flow. And I've arbitrarily chosen that between 950 and 969 hectopascals, so something that you would expect to see a hurricane of moderate hurricane intensity, category 2, 3, maybe 4 on the Saffir-Simpson hurricane wind scale. This gives us an 850 to 300 hectopascal steering layer. And to first glance, to first extent, the pattern looks pretty similar. We have a subtropical ridge to the disturbances northwest. We see some sort of cyclonic flow near the disturbance itself, intense low in the Gulf of Alaska with fast west to east flow in this layer average across the northern Pacific Ocean, extending to the Pacific Northwest and British Columbia, with a trough in the central United States here. It's not always this similar, and there are a lot of differences in terms of the actual wind speeds, noting that here you're getting to more faster wind speeds, given that you have a larger extent of orange and red shaded as compared to the previous diagram, which makes sense. If you start to get up to higher altitudes, when you look into the mid-latitudes, given that wind speed typically increases with height in the mid-latitudes, you're going to include faster winds at those higher levels within your steering flow. So this concept that you see here, this deep layer steering flow in this case that extends over much of the depth of the troposphere, or the low layer, the shallow layer steering flow on the previous slide that extends just a little bit above the planetary boundary layer, depending upon the intensity of the cyclone, is going to do a reasonably good job of explaining where you would expect the cyclone to go over the course of the next 1 to 2 days. Of course, this wind changes over time, so you'd have to factor that in if you were creating a forecast based off of this. But nevertheless, this helps to illustrate that large-scale flow that we can expect would predominantly steer the tropical cyclone. So summarizing here, tropical cyclones again are largely steered by the large-scale wind. 60 to 80% of a tropical cyclone's motion can be explained by this large-scale wind, particularly that in the free atmosphere. We introduced this idea of a steering flow, which is averaged over a large horizontal region and vertically weighted to a given depth based upon the intensity of the tropical cyclone across the cyclone. And again, just noting once more that this is a function of the cyclone's intensity. More intense cyclones are steered by a deeper layer averaged wind than our weaker cyclones. So having explained this, which is the single biggest contributor, our next video is going to get into our second biggest contributor, which is something known as the beta effect. And we'll talk about how that helps to modify where a tropical cyclone is going to go relative to the wind field that we have illustrated here. But until then, thanks for tuning in.